Okay, welcome everybody. It's my great pleasure to introduce Panagiotis Konstantis, who will speak about classification of vector bundles over manifolds, a hot stew with a bit of homotopy theory, differential geometry, and algebraic topology. Oh.
Okay, yes, thank you very much, Thomas, for the invitation. I like the format very much. So as far as I understood, it is a format for students. So I prepared this for students. So if someone is like more advanced, they have to excuse me because I keep it as low as possible to get to this point to understand what I did in some works of which I wrote lately. And the topic is, as it says already, it's the classification of vector bundles over manifolds. And I like this topic very much. It's one of my research topics because there, as you can see, a lot of topics in math come together, like homotopy theory, differential geometry, and algebraic topology. I like all the three of them, and if you can combine this, it's more fun to do it. And I would like to start with the motivation. So as you can already read, I want to try to give you a good reason why to study vector bundles over a manifold. And so the first reason is simple, that for example, if you know what kind of vector bundles do you have over your manifold, you can decide if your manifold has certain geometric structures like almost complex or almost contact, right? So if you have a tangent bundle and you know there is a complex vector bundle such that if you look to its realification, meaning that you exchange the fiber from Cn to R2n, and then it comes out that this is your tangent bundle, then you found a almost complex structure on your manifold, which is interesting because it's an additional structure. And also I think almost complex structures in general are very interesting. And the same game you can play for almost contact and other geometric structures. So this is maybe one reason why to study vector bundles. The other reason is also very interesting because by the Whitney embedding theorem, you can embed every manifold into certain Rn. But and I think if you have an oriented manifold, you can at least embed it to R2n minus 1 if n is the dimension of the manifold. But if you want to push this dimension of the ambient Rn lower, you have to make sure that you, so this is not always possible. And if you do this, you need a special kind of normal bundle of your embedding. Right, so you embed your manifold there, and you want to push it lower, you need your normal bundle to be of special kinds. And if you know that, if you maybe understand the vector bundles of your manifold and you see, okay, there cannot be such kind of normal bundle, then you know this manifold cannot be embedded into this specific Rn. Right, so this is also maybe a nice property, a nice thing to know. And of course, the third point is that you can produce other manifolds out of vector bundles of your manifold. And this is called sphere bundles. So if you take a vector bundle and you take in every fiber, instead of Rn, you take its sphere. So let's say you take a Euclidean bundle metric on your vector bundle, and then you take just in every fiber instead of Rn, you take a sphere, you get a so-called sphere bundle, which is again a manifold. And usually these are very good examples to test things or to produce counterexamples to certain assumptions. And the thing is that if you know your manifold and the vector bundle, you almost know, you understand very, very good the sphere bundles of the new manifold. For example, an interesting thing is on part 3, if you know about exotic spheres. So this was a very big thing in the 50s and 60s, where Milnor discovered an exotic sphere. This is a sphere which is homeomorphic to S, so in this case S7, but not diffeomorphic. So it has another differentiable structure. This was unknown to exist until Milnor came, and actually constructed it as a sphere bundle over S4. This is an S3 bundle, as a sphere bundle over S4. So you see, this is there are a lot of quite interesting examples of sphere bundles. All right, so what we want to show is to understand this vector bundles over a fixed manifold, and we want to classify them in a sense that you can also name the invariants, and also this invariance should be more or less computable, right? Should somehow can compute them and use them in a good way. And this is a thing where first you think this is a topic of differential geometry, but then you can switch this classification into a thing of homotopy theory, and this is very interesting. And I'm trying to do it in a very basic version, and therefore I assume that M is a compact connected oriented manifold. But everything what I'm doing today, or at least in the next pages, is also valid for non-compact manifolds, and is actually also valid for CW complexes, most of the things. Right, so we take this compact connected oriented manifold, and we take a real vector bundle over M of rank K. So I didn't define what a real vector bundle is, but it's the usual notion, right? You have a covering of your manifold of open sets, and you demand that over every open set, the vector bundle is trivial. So this is something like the open set times Rk in this case. And you demand also that the transition functions of two overlapping open sets of your covering should consist of linear transformations of the fiber. Okay, and now this comes, so this is an important part, what will follow, is that you have a compact manifold. You can consider this vector bundle of your manifold as a subbundle of a trivial vector bundle of your manifold, Rn, if n is big enough. And this mimics more or less the proof from Whitney-Bedding theorem for compact manifolds. Namely, how do you get this f? Or let me just quickly explain how you get this f here, which defines actually this E to be a subbundle of M times Rn. So let me create a new layer, and oops, no, sorry, I'm here. So so maybe I was a little bit too fast. So what is this f? This f is a map from E. So if you have a vector bundle E, this is itself also a manifold. So you have a map E from Rn, such that if you restrict it to every fiber, which is again a vector space, this map should be a monomorphism. It should be a linear injective map for every P, right? This is what you have here, this map. And this can be constructed as follows. Well, you know that you have this open covering of your manifold of this open covering of M, and you know that over every this M here, so this is what we denote by E restricted to EI. This is something like UI times RK, right? This is the trivialization. And of course, from here, you have a projection map to RK. So this is the projection map. And this whole map from here to here, let's call it phi I. So I'm sorry that maybe it's not very good. So my handwriting here differs from here because I'm using a different system now, which I'm not used here, and that's why it looks a little bit bad. So you have here this map, and you know this map here is on the fibers, is ejective, it's just a projection here, right? And you can extend this map to a map on whole E. So you can consider this map as a map from E to RK, and you know over E restricted over UI, you know it's fiber-wise an injective map. So you have this phi, and this is of course a finite covering because M is compact. You can choose it as a finite covering, as a finite cover, sorry, open cover. And then this F define it as just taking phi1 until, let's say, phi l, which goes from E to Rk times Rk L times. So this is something like RL times K, and this is our N, which I had before. Right? And then you can check every property. So this is, again, if you restrict it to every fiber, this is an injective linear map, and this is how you get F. Okay, so it's almost similar to the proof of the Whitney-Bennett theorem. Okay. So this is this one here, right? And if you have this map, you can now define a map from M to the so-called Grassmannian of R to the big N. And what is a Grassmannian? It is just the set of k-dimensional subspaces of Rn, but with a topology on it. And I don't want to explain how the topology comes, so I don't want to explain it in detail, but you can define it as a quotient space from the so-called Stiefel manifold. So this is a quotient space. It inherits a quotient topology of the Stiefel manifold. So you have here topology, and M has also topology. And what you do is you define now a continuous map, which does the following. You take a P on your manifold, and you just map F to the EP, which is now a k-dimensional linear subspace because F is injective on the fibers of Rn. So this is the sign for me for a subspace, right? And in that way, you get a map from M to the Grassmannian. And so you see this number big N, this can differ from vector bundle to vector bundle of your manifold. And to get rid of this dependency, because at the end you want maybe just one space to describe all of your vector bundles, you eliminate this number M by taking just here instead of Rn, R infinity. So you have this chain of inclusions of Rn's, and then you can just more or less take a union of it and a special topology on it. And if you do that, you get also a chain of Grassmannians like this, the inclusions here. And you can also define this here as some kind of limit of this chains here, this Grassmannian. And this is what we call the BOK. So the O here stays for orthogonal group, because every vector bundle, every real vector bundle, you can say that the structure group, so whatever this is, for you who know what a structure group is just the orthogonal group. And so this is called the classifying space for real vector bundles or of vector bundles with orthogonal group as a structure, right? Okay, so we take some limit process here, more or less, if you like, set theoretically, honest topologically. We take here a limit just to get rid of the dependency of N from E. And what's interesting about this space is the following. So the isomorphism classes of real k-dimensional vector bundles, right? This is the only thing which are interested for us. We just want to understand vector bundles up to isomorphism of vector bundles. So they correspond now bijectively to homotopy classes of maps from M to this Grassmannian, right? This is a very nice theorem. And this is the transition from, if you like, now in this case, from differential geometry. Actually, this is not only a part of the differential, but here, because everything is a manifold and smooth vector bundles, this is just from differential geometry into homotopy theory. Because every vector bundle corresponds uniquely to a map from M to BOK. And if you change the map to a homotopic map, this will just change this here to another vector bundle, but which is isomorphic to the one we started with, right? So the thing is, if you go here from one vector bundle to another one, which is isomorphic, you go here from one map, which is homotopic, to another map, right? This is the one-to-one correspondence. And now sometimes homotopy theory is a little bit more, so sometimes it's difficult to compute things, but sometimes it's also better in homotopy theory to compute things. And in this case, this is really So in my case, it was easier to compute this one here to get this one here. And of course, you can do this not only for real vector bundles, you can play the game for all different kinds of vector bundles. For example, complex vector bundles. This, of course, when you replace the fiber of RK with CK. And therefore, because it's a vector bundle with a unitary structure group, we write BUK for it. And even oriented vector bundles, which will be of most interest for us in this talk, I write this here with a plus. Then you have also a Grassmannian, which you call BSOK. And what differs from here is just you're not only taking linear subspaces, but you take linear subspaces which are oriented. So oriented linear subspaces here. Get also a Grassmannian of oriented k-dimensional linear subspaces. And this is then with the same procedure here, our BSOK. So you don't have to understand in detail what this thing is. The only thing you have to keep in mind is, okay, you can translate this problem into this just by looking to homotopy classes of maps from here to here. And you can have a very explicit correspondence from here to here in the following way by using the so-called universal bundle. So over all these classifying spaces, there sits a universal bundle, not the same, but for each classifying space, you get a universal bundle. And this universal bundle established this isomorphism or this bijection here just by pullback, meaning that you have this k-dimensional vector bundle, let's call it E hat over BOK. And if you take a map here, a homotopy class, so you take a representative of your homotopy class here, let's call it G, and you pull it back, this bundle here, right? So if you pull it back by G, you get a bundle over M. And this isomorphism class corresponds to this homotopy class under this, this theorem here, right? So homotopic maps pull back E hat to isomorphic vector bundles in that thing. So if you know your universal vector bundle and you know your map G, you can reconstruct more or less the vector bundle, any vector bundle over your manifold. Okay, let's take an example and take maybe one of the easiest manifolds we have, the sphere. So what if I replace M by the sphere? So I'm interested in the oriented k-dimensional vector bundles over Sm+1. So by the theorem above, it's just the homotopy classes of Sm+1 into BSOK. And this is nothing else than the n+1 homotopy group of BSOK. Right? This is a topological space, so I can consider its homotopy group. And then by a certain long exact sequence in homotopy theory, you can establish this isomorphism. So I don't want to get into detail, but for those who knew what I mean, is just taking the long exact homotopy sequence of the principal bundle, which sits over BSOK, then you get this isomorphism here. But you can just accept that there is an isomorphism between here and here. And here is really the special orthogonal group of degree k. Right? So Pn+1 of this is Pn of this. And now this comes to a very interesting fact. If k is bigger than n+1 in this case, then this group here is independent of k. We say that we are in a stable, so-called stable range of homotopy groups. Now, this is very interesting because then this n, this homotopy group depends only on n, and Bott proved there's a certain periodicity in there. So it depends only in this range only on the parity of n modulo 8. This is the so-called Bott periodicity, and you see here the values, right? So you see here, for example, over a sphere of dimension 8L+1, right? There can be only two vector bundles, the trivial one and the one which is not trivial, because it is a two factor. And here you get Z ones and here you get Z ones. keep in mind that we are in the stable range only, right? Okay, and as a corollary, let me phrase this one here. So if you take, for example, an embedding of a sphere SL plus 1 into a manifold of dimension 16L plus 10, so the numbers here may look arbitrary, but trust me, this situation is let's say it's real. It happened. So, for example, in this business of exotic spheres and stuff like that, which was done by Milner and Cavere in their famous paper, they use stuff I'm telling you here now, especially this one here. And then, so what I want to say, if you have an embedding of this sphere in this manifold of this dimension, then the normal bundle of this sphere must be trivial. This refers to the point 2 I had in the motivation section up there. And this is just a simple computation that if you have these numbers here, you are just in the case where n is 8L plus 4, and then you're in this case here, and you see there is no other vector bundle other than the trivial one, if the manifold has dimension bigger than 16L plus 1. And if you have a manifold which embeds into another manifold with trivial trivial normal bundle, then you can do a very nice construction, where I will tell you later, the so-called Pontryagin Thom construction, and we will see later why this is so beautiful. But this is a very interesting effect, I think, just to purely by this number and what periodicity you know that this vector bundle has to be, this normal bundle has to be trivial. Okay, I forgot to say, if there are any questions, you can always speak out and just interrupt me. There's no problem. It's no problem for me. Yes, for complex vector bundles, the situation is easier. You again have here BUK, and this is isomorphic to pi n UK. And for 2k bigger than n, the groups are again in the stable range, invariant, independent of k. And then again, a Bott periodicity kicks in, and this is far easier, much easier here. This means that the homotopy groups of even dimension vanish, and of odd are always Z. So there's only 2 periodic here, and this is here 8 periodic. Okay, let me state another example of this classifying spaces. So this concerns complex line bundles, which are very omnipresent in algebraic geometry, or in complex geometry, let's say. So of course, if you have like, so you know maybe what CPN is. CPN is just, if you like, the lines of Cn plus 1, right? This equivalent. So the set of lines in Cn plus 1 gives you CPN. And the same you can do, of course, with C infinity, right? So if you have C infinity and you look at the lines in C infinity, you get just CP infinity minus 1, if you like. And this is again CP infinity. So it's not that easy, of course, but you can do the same constructions with this chain here, take a certain limit, topological limit, then end up with CP infinity. So if you like, the Grassmannians of one-dimensional linear subspaces of C infinity is CP infinity. And then we call CP, we know that CP infinity in topology, so if you take advanced course in topology, we know this is a so-called KZ2. And what is the property of such a KZ2? So this is a space, this is a topological space where all homotopy groups vanish except for 2, and in 2 it's just isomorphic to Z. So pi 2 of KZ2 is Z, and all other homotopy groups vanish. This is called an Eilenberg-MacLane space. And then if you just plug it into your bijection between vector bundles and homotopy theory, you know whatever you have an Eilenberg-MacLane space here, K, let's say for any group, let's say KZN, and if you plug it in here, you always get the corresponding cohomology groups with Z coefficients. In that case, you get the second cohomology group with Z coefficients. And you know a little bit more, you know that this isomorphism is just given. If you take a line bundle over a manifold, this isomorphism is given by just mapping the first Chern class to H2. So I will say a little bit something about characteristic classes later, but this is just a certain cohomology class which you can assign to L with certain properties. And this lives in that case in H2MZ. So this is a very nice correspondence because you know every element here in this group can be represented as first Chern class of your line bundle. And the same story goes for real bundles, which is a little bit easier. So there you have just, instead of CP infinity, you have RP infinity, and RP infinity is a so-called KZ21. And the corresponding cohomology group is just H1MZ2. And the correspondence is between L and the first Stiefel-Whitney class, which I will explain later. Okay, but these are just the optimal cases, if you like, for this situation. Because in general, it's really difficult to compute these spaces for arbitrary manifolds and for arbitrary K and stuff like that. But as I already said in the abstract, in low dimensional, it's quite feasible to do something like that. And there are lots of variants in low dimensions with certain cases. I don't want to show you all of them, but I want to show you one of them, which is for this talk important. And this is a theorem of Woodward. So then here will come maybe a lot of stuff a lot of people don't know, but it's not important. I tell you what is important about this theorem. And let us see what this theorem says. It's from Woodward from 1981. And he assumes that X is a connected CW complex. So if you like, I don't talk about CW complexes here, but I just wrote it as he wrote it in his paper. So you can just think of, in that case, of a n-dimensional manifold where n is 4 and 6 for X here. Okay, and then you can define a certain map from the vector bundles. So you have here now oriented n-dimensional vector bundles over your n manifold, where n is only 4 and 6. And you map it to this direct sum of abelian groups here, to cohomology groups. And this is defined by taking certain characteristic classes. This is called the second Stiefel-Whitney class. This is the first Pontryagin class, and this is the Euler class. Again, it's not important what they are. It's just important to understand there are cohomology classes, certain cohomology classes associated to a vector bundle in this group here. And then he says, okay, well, I can understand this image, right? I can understand the image of alpha, what it is. This is some complicated thing. So for the people who know, I can explain at least the first line. So what you take here is a mod 4 reduction of your coefficient group. And this is called the Pontryagin sphere. So this is an equation in H4 with coefficients in Z4. This is for n equals to 4. And here is a similar. So this is the mod 2 reduction of Y, and this is the mod 2 reduction of Z. But you have only to know that one can understand the image of alpha completely. So we know on which set on the left side this map here is surjective. But you can also say something about injectivity, and this is part B. He says that alpha is injective if H4 and Hn have no two torsion. For example, if you take X as a 4 manifold, H4 has never two torsion. It's always Z if you take an oriented manifold. So I would say it here that X is an oriented manifold. Or if you take X as a 6 manifold, an oriented 6 manifold with vanishing out integer cohomology and is compact, then also both of these conditions are fulfilled. They have no two torsion. In that case, alpha is an injection, and then you have a bijection from here into its image. And in that case, you understand the vector bundles completely, because these things here are fairly easy to compute for a vector bundle. So they're computable. These things here. So this is kind of, well, you enumerate your vector bundles, right? and you know how the enumeration goes in terms of characteristic classes. And part C is just an existent result. So if you take any element of the set and cohomology group with coefficients in Z2, you just can find a vector bundle E with that second Stiefel-Whitney class if this condition is fulfilled. And this is again, this is so-called a cohomology operation, and this is the certain Box-Stein homomorphism. But it's again, it's not important to understand this. It's just an existence result. And you see here, by the way, for the cases n equal to 3 and 7, you can do exactly the same with different conditions on the image, but with same claims here. But then we have covered the cases 3, 4, 6, and 7. For 2 and 1, it's easy. I didn't mention them. It's not important. But you see, the case 5 is missing here, right? So the k of n is equals to 5 is missing, and I give you can give you a rough reason for it why it's missing, because a classification of that kind doesn't work for S5. Because if you want to characterize vector bundles by certain cohomology classes, this will not work in S5, because in S5 the only non-trivial cohomology groups are concentrated in degree 0 and in degree 5. And you can show that any characteristic class in degree 5 vanishes. So actually, the only possible candidates for characteristic classes in degree 5 are the Euler class, this vanishes, and the fifth Stiefel-Whitney class, this vanishes also for every vector bundle over S5. But we know, I didn't write it here, but we know, I tell you later a little bit about that, because of this classification here, we know that, let me write it in a different color. We know that the vector bundles, so in that case, oriented vector bundles of rank 5, this is what here is interesting. So you're only interested in the vector bundles of the rank which is equal to the dimension of the manifold, right? Over S5 is just pi 4 of SO5, right? You have to shift this here by 1. And now, if you know a little bit of Lie group theory, you know that this here, so the universal cover of this one here is spin 5, and this is something like the symplectic group in dimension 2, and you can compute that this here is just Z2. So over S5, there must be 2 vector bundles, oriented vector bundles of dimension 5. Of course, there's a trivial one and a non-trivial one. But we know from other reasons that the tangent bundle of S5 is not trivial, right? So there are different, can use for them different statements, like Milner has some statements where he says that the only sphere with trivial vector bundle is in dimension 1, 3, and 7. These are the only spheres which have trivial vector bundle. All the other spheres don't have trivial vector bundle. So this means that the other element here, the non-trivial element, is exactly the tangent bundle of the sphere, but it cannot be distinguished by the trivial bundle through characteristic classes, because the characteristic classes for the trivial bundle are always 0, and the same goes for the tangent bundle of S5. Right, so this thing is not possible. Okay, so before understanding this case n equal to 5 and how it has to do with the so-called Homotopy groups or Homotopy group, I would like to present you a side dish, and this is just a small section about characteristic classes, and it's not like the usual way to. Actually, I want only to explain the Euler class and the first degree Whitney class, and it's not the usual way characteristic classes are introduced. It's just my way to do it because it fits for my purposes much better, especially for an audience which is not that which doesn't have a lot of knowledge about characteristic classes. So let's talk about the Euler class. This is the thing I wrote here. So what is the Euler class? So let's take an oriented vector bundle E over M over an oriented manifold. And then we know that we have always a special section on this vector bundle, which is called the zero section, right? Just map every point of M to the zero of the correspondence vector bundle in this fiber, right? So over P, it's such a zero in the fiber EP. And this gives naturally a submanifold here, right? So the zero section is the image of the zero section is a submanifold, and it's naturally diffeomorphic to M, right? This is just a diffeomorphism here. So we can see that we can just assume that M is embedded into E. So every vector bundle, of course, its total space is again a manifold, and M is in that way canonically a submanifold of E through its zero, through the image of the zero section. Now let's take another section. Then there is a theorem in topology which says if you take any section of this vector bundle, you can make it always transversely to the zero section. And what means transversely? Transversely means for every point in the intersection of your section here with your zero section, the tangent spaces in this intersection point, they have to add up to the tangent space of your ambient manifold, which is like the tangent space of E in the point V. So this has not to be a direct sum, but the sum of vector spaces should generate your whole vector space here. So this is a schematic picture of the situation. Well, this is your zero section, and this is another section here, which intersects the zero section transversely, right? So intersects in these points, and you see here the tangent space of the image of this section here is just this blue arrow, and here is this blue arrow, and this spans, of course, the tangent space of E in that point, right? And this goes for every point here. So let me show you. Let me show you what is not a transversal intersection. Let's take just this image here. This one here. Just copy it to the other layer and use it here. So what is not a transversal intersection? For example, this one here. If you go here, this one here, or even that one here, right? This is, of course, not transversal. Why? Because if you look at the intersection points here, this intersects here, and the tangent space of the red line is the same as the tangent space of the black line, and it's just that. This doesn't span the two-dimensional tangent space of E in this picture, right? And also here, all these points here, of course, have the same property. But you can always deform this, and this is really amazing, because you can. The theorem of transversality says you can just take, you can deform this section epsilon close to this red line, such that it's transversal. So you can in every epsilon neighborhood of the image of this red line, you find another section such that this section intersects the zero section transversely for every epsilon, right? And you can think of how roughly this works. You just take at this point here, which destroys the transversality. You just make a little bump here and produce two new intersections, but they are transversely. And here you can do the same, right? Go here a little bit and up here. And you can do it epsilon close to the red line. And why is transversality so nice? Transversality is nice because of the one and only reason that you can show that this is actually a fact of just you can generalize this. If you have a big manifold, let's say M, and two submanifolds N1 and N2, and they meet transversely, this means exactly the same here. The tangent spaces add up to the tangent space of the ambient manifold in intersection points. If you have this, then you know always the intersection points are again itself a manifold, and that's really nice, right? If you have something that intersects, and again in a manifold, this is very good to work with. And the main reason for that is just that if the transversality condition just enables you to use something like the implicit function theorem to produce charts for the intersection set to be a manifold, right? So that's why transversality is always very nice to have, and you can always achieve it. This is also very nice. I mean, you can in certain circumstances, but if you have, for example, two manifolds which don't intersect transversely, you can make them just a little bit by deforming them to meet them transversely. This is very nice. And you can also know what the dimension of this intersection is. If you see here, the dimension of the intersection is just the dimension of the intersection of these two spaces, right? So if they're not the direct sum, they intersect in some vector subspace, and the dimension of this vector subspace is the dimension of your intersection. And you see here, E has dimension 2 in that picture. The red line has dimension 1. The black line has also dimension 1. So the intersection here should be of dimension 0, right? And points have dimension 0. In general, it's just the dimension of M minus the rank of E. This is the intersection manifold. Well, that's nice because you get a submanifold not only of E, you get a submanifold of M because the intersection lies in M in the 0 section, in the image of the 0 section. But this, of course, you can identify with M itself. So you have a submanifold in M, and if you take the so-called Poincare dual. So I don't want to, so if you know it, it's good. If not, just accept that you can, if you have such a submanifold here in M, you just can take a so-called dual, and this is an element in cohomology class. And in that case, it's an element in cohomology class in dimension of the rank of the vector bundle, right? If your rank is 5, then you get an H5 of M with coefficients in Z something. And this is called the Euler class. So the Poincare dual of this manifold here, which comes from an intersection of two transversely submanifolds, this is called the Euler class. And why is it called Euler class? It's called Euler class because if you have a cohomology class like the Euler class, and if you have a homology class, then you can pair them and get a number back. So what you have here, for example, if you take for your vector bundle just the tangent bundle of your manifold and take its Euler class and pair it with the fundamental class, this exists always if you have an oriented manifold. So this is a homology class in degree n. This is a cohomology class in degree n. You can pair it by the Kronecker pairing. You get a number in Z, so you get an integer out of it. And this happens to be just the Euler characteristic. So this is the alternating sum of the Betti numbers. And the Betti numbers are just the dimension of HI with coefficients in R, right? Or if you like, it's just the dimension of the free part of your ith cohomology group. Okay, and out of this construction here, or out of this definition, if you like, so as I said, usually Euler classes are defined in a very different way. But with this approach, you can see the following very quickly. You see, if E admits a nowhere vanishing section, right? If you have a section which is nowhere 0, this is not always possible, then you see the Euler class must be 0, because if you take a section which is nowhere 0, let's say this line here above, then this intersects this line here transversely, because this condition is empty, right? For all points in the intersection, where when there's no intersection, this is empty, and this is also considered transversal intersection. Then you see that the 0 locus of that is also in that case empty, and you can translate it in the sense that the Euler class must vanish, right? So you have always a direction if there exists a nowhere vanishing section, then your Euler class is always 0. The other direction is not always true. I will say in the end of the talk something about it, but at the moment you can say that if the rank of your vector bundle is the same as the dimension of the vector bundle, then the Euler class is 0 if and only if there is a nowhere vanishing section. For example, this is true if you take always E as the tangent bundle of M, then this condition is always fulfilled. And if the Euler class is 0, then you have a nowhere vanishing section. For example, this is always the case when the manifold is odd dimensional, right? If you have an odd dimensional manifold, your tangent bundle has always a nowhere vanishing section. Your tangent bundle always splits a real line bundle up, And this is just in odd dimension. This alternating sum here is always 0 if you use Poincare duality. So Poincare duality here establish an isomorphism between hi of m with hn minus I of m when n is the dimension of m. Using that, you see this alternating sum is 0.
So, Taki, can I ask a stupid question?
Yes.
So I didn't understand. So this definition of the Euler class. So for this definition, you're using a section S, right?
Mm-hmm.
So how does the Euler class depend on S? It doesn't depend.
It doesn't depend, but there's also a result here. So if you take another section, there's a very good point which I should have mentioned. If you take another section here, you get of course another set manifold here as a 0 locus, but the Poincare duals would lie in the same cohomology class. Why this is the case, I would go too far maybe to explain this.
Yeah,
but
it's
this
okay.
is,
It's okay.
Yeah, it's a good point. Yeah, this does not depend on this section here, on the transversal section. Yeah, thank you.
Thank you.
Okay. Well, okay, this is the one thing I wanted to explain you, the Euler class, because we will need it later. And the other thing is spin structures. And again, this is really presented here a little bit more exotic. So if you learn spin structures, at some point you will learn it through using some principal bundles and taking 2-to-1 covers over your frame bundle and stuff like that, and then you get a spin structure and stuff like that. Everything this can be translated into the thing I show you here, and I chose this one here because it fits more to the flavor of what will come next. Okay, the Stiefel-Whitney class will play a certain role in this part here. And what are Stiefel-Whitney classes? These are cohomology classes associated to some vector bundle, to any vector bundle, real vector bundle. And the ith Stiefel-Whitney class lives in the ith cohomology group with two coefficients. And let me show you what the first Stiefel-Whitney class is. And to understand this, you have to understand first a characterization of orientability of a vector bundle. And you can show that a vector bundle of a manifold is orientable if and only if every loop in your manifold, so what is an orientation? You just take an orientation in every fiber of your vector bundle, and then it's called orientable if you can achieve the following with this orientation you took there. So if you have a loop and you go one round, the loop once around. Here I have this loop alpha, and you go once around. You have different orientations here, which they shouldn't change, right? Right, the orientation shouldn't change because the orientation here, from here to this point here, there's a homotopy between these two orientations from here to here. That's just given by the curve. So the orientation should be always the same here. And if it's orientable and you go once around, you should end up with the same orientation. If this is not the case, your vector bundle cannot be oriented. So your vector bundle cannot be orientable, right? So if it's orientable, and this is a necessary and sufficient condition, if it's orientable, you can take any loop here and look at the orientations. This should stay in the same orientation class. And if you close the loop, you should end up with the same orientation as a start. A prominent counterexample is, of course, the Mobius band, right? So if you like, the Mobius band is a one-dimensional vector bundle over S1, which is not orientable. Right, this is this famous thing that when you go once around, the orientation shifts. Right, and this gives a homomorphism. This is all things you have to prove, of course. But for example, in the book of Hedger about vector bundles, it's very nicely explained. I can recommend it very much to read these things there. So this gives a homomorphism in that way that, so of course, if you have here a loop and you go to a homotopic loop, the same thing should hold for the homotopic loop, right? If you go once around, the orientation fits. This should hold for every homotopy, for every loop which is homotopic to alpha. And thus this produces a map from here to here, which is a homomorphism. And this homomorphism just assigns 0 if the orientation is preserved under the homotopy class of the loop, or it's 1 if it's not preserved. This gives a homomorphism here. And now just a effect of group theory, because Z2, the group of 2 elements, is abelian, this map must factorize through the abelianization of pi1, right? Because this is abelian. The image of the group here just only takes care of the abelian part of this group, right? Everything else you can't detect because this is abelian, right? And what is the abelianization of pi1? It's just the first homology group, right? So this means that this map factors through a map from here to here. So it gives a homomorphism from the first homology group into Z2. And this represents then an element in the first homology group of M with coefficients in Z2. And this homomorphism is called the first Stephen-Whitney class. Okay? So keep in mind that you can have 2 loops where, so to say, the orientation, it's okay. So this gives just a homomorphism here, and this represents a class in H1. And if this class is 0, that's what I wanted to say. If this class is 0, then your vector bundle is orientable, right? Because if this class is 0, then this thing holds, and then it's orientable by this fact here. Okay. And so note now for our purposes one special remark. If you take S1, you have only 2 real vector bundles over S1 for any rank of the vector bundle, because it's classified by pi1 of BON, not SON, BON, and this is just isomorphic to pi0 ON, so it's isomorphic to the connected components of ON, and this is just Z2, right? It's just, it has 2 identity components, ON, which are characterized by determinant 1 and determinant -1. And of course, the determinant 1 component here are the vector bundles over S1 which are oriented, and the other ones not. And they're just distinguished by the Stephen-Whitney class, as I said now. So there are only 2 vector bundles over S1. It's just the trivial vector bundle because it's oriented, right? And the Mobius vector bundle if you like, so a kind of Mobius vector bundle. So a vector bundle, a real vector bundle, which is not orientable, right? But you know, if you have always a vector bundle over S1 which is oriented, then you know for sure that it's a trivial vector bundle. Okay, this is the first Diffie-Whitney class. It gives you information if your bundle is or can be oriented or not. Okay, in the last 4 minutes, I want to try to explain you what then a spin structure is. So let's assume that we have now a oriented vector bundle. So we know that the first Diffie-Whitney class vanishes, right? What can we do now? Let's talk about first of the so-called framings of vector bundles over S1. So what is this? If you have a vector bundle over S1, this will be now necessary to explain you what a spin structure is. If you have a vector bundle over S1 and it's oriented, we saw then that it's trivial, right? And now you can choose a trivialization. What is this? So if your vector bundle over S1 is of rank k, you can choose k sections of this vector bundle such that in every point of Sn, this forms the basis of EP. And this is for every p. This is possible because we know the vector bundle is trivial, so we can choose a trivialization, right? And for me, maybe for some other authors, this is not a difference, but for me, a trivialization and framing are different things. So I just told you what the trivialization is. And a framing for me is a homotopy class of trivializations. And how do I say that two trivializations are homotopic to each other? Well, if I have two trivializations and I take a homotopy between them, I demand that this homotopy should be in each time step should be a trivialization again. So it's trivialized. So it's this homotopy should be, it's like given by trivializations, the homotopy, right? In every step, they should pass through a trivialization. And if I end up with the given ones in the beginning and the end, then they are homotopic. Then I say they are homotopic, and then I say that they correspond to the same framing, right? The framing is always a homotopy class of trivializations. And there are exactly two framings over of a trivial vector bundle over S1, because you can see it as follows. You can choose a trivialization, and then any other trivialization is determined just by a map from S1 to SOK, right? So you can just, for example, take a Riemannian bundle metric, and then you can make Gram-Schmidt, and then you can always you can say that if you choose two trivializations, which are orthogonal trivializations, right? If you have two of them, they will differ by such a map, because you can go over every fiber. You have two orthogonal frames, and they must differ by a metric of SOK, right? So in that way, you get a continuous smooth map from S1 to SOK, and this defines an element of pi1 SOK. And since everything needs only to be unique up to homotopy, it is enough to understand this homotopy class, and this group is just Z2. So if k is bigger than 3, this fundamental group here of SOK is just Z2. This means there are just exactly two framings over of a vector bundle over S1. So if you like, I think in a more modern language, it's called the set of framings is a torsor over pi1 SOK. This is, I think, a modern way to say it, right? So this is somehow an affine space over pi1 SOK, right? If you fix one trivialization, every other is determined by this one here. And it's always important to know that these things are only to be unique up to homotopy, right? Because the framing is a homotopy class of trivializations. All right, so let me, before going to break and explain the spin structure, let me just show you a picture, because maybe it's a good thing to end. What are the two framings? So let's think of S1 embedded into R3, and then we can take the tangent bundle of R3, which is a trivial vector bundle, and look it over S1. Okay, So, and then you can picture the two framings here of this trivial bundle over S1 as follows. Well, you take here in every point, you take, like, for example, the standard basis of R3 as a trivialization of every point. It's the same, it's just E1, E2, E3 for every point. Or you can just take the, so this is the one framing which corresponds to the 0 here, if you like. Or you can take the other one, which is like this. It's also a framing. And what you do is the following. You take this, what you do is you rotate this frame, this two vectors here in the plane orthogonal to the tangent space of your circle, right? If you go the circle around, you have the normal space of this circle is a plane, right? And you let them rotate in this plane, right? As you go around. And you see here, if you go round, 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 so this will fall down, right? This will, and this point will show here. And then if you rotate it further, it will go down here, here, and then up here again. And this is exactly the framing, the other framing of this vector bundle, right? So yeah, you can also do it with your three fingers, right? So you can go around, round, round, and see if you do something like that, you will see that this fits. And this is not homotopic to this one here, because roughly you go in this normal plane, you rotate your two vectors once, and this is not homotop. This is not homotopically trivial. You cannot extend this to the disk which S1 bounds. All right. So I think it's time for a break, right, Thomas? Okay.
Yeah, that's good to have a little break at for, well, I think 25 minutes. That ought to be enough. Are there? Well, let's thank you already for the first time.
Okay.
I enjoyed it a lot.
You're muted, Tom. Yeah.
I am muted. Are there any questions at this point? Okay. So let's have a little break. Maybe you can stop sharing so that we can just see each other. I'm gonna grab a tea and I'll be right back, and I will pause the recording during the break.
Okay. Should I wait or?
Oh, you can go.
All right. I think this is this one here. Okay. So let's continue. Yes, I want to try to explain you what spin structures is in my world, and this is the following. So what we did so far here, if you have an orientation if a vector bundle with an orientation over a manifold, then because of the thing I told you here, then you know that over the one skeleton of your manifold, the bundle must be trivial, because the one skeleton is roughly a union of circles of S1s, and over every S1 the vector bundle is trivial, and because it's orientable. Okay, and if it's over the one skeleton, if it's trivial over the one skeleton, you can just take a framing over the one skeleton, and you can ask, can I extend this framing to the two skeleton of this manifold, right? This is a question which you can ask in a manifold. And if this is the case, if you can take a framing of your vector bundle over one skeleton, such that it extends to the two skeleton of the manifold, then we say that E is spinnable and has a spin structure. So this is a spin structure for me in this talk. Just take a framing of the vector bundle over the one skeleton, and if this is extended to two skeleton, then it's called a spin structure. And you can translate this into a characteristic classes. And this is the equivalent to say that a spin structure is something where the vector bundle has a trivial first chunk class and a trivial first Stiefel-Whitney class, and a trivial so-called second Stiefel-Whitney class, which I will not explain here, but you can express this in these two terms. Okay. So, but for this talk, it's only it's enough to know that this is a spin structure. And you can see here, for example, this framing here above, this extends, of course, to the disk, which is bounded by this S1, because it's just the section by the standard basis. But this here, which twists around, you cannot extend to the inner part, because this one here, this framing here, is represented by the non-trivial element of this group. And if this map is homotopically non-trivial, you cannot extend it to any disk, right? Otherwise, it would be homotopically trivial. Okay. So the vector bundle with this framing has a spin structure and does not. All right, so now let's come back to dimension 5. So I told you now what the Euler class is and what a spin structure is, and this is now important for us. So maybe I just go 1 second back to the theorem of Woodward, where he just took an n manifold with n equal to 4 and 6 and looked at dimension, the oriented vector bundle of dimension 4 and 6 over this n manifold. Okay, so I want to do the same, but now in dimension 5. So I'm interested in the classification of oriented rank 5 vector bundles, real rank 5 vector bundles over compact, oriented, and connected 5 manifolds. And the case where M is not spin, so this is a big difference. S5 does not fulfill this condition, so M5 is spin. The case where M is not spin was covered by Czarek and Wanzura in 1993. And the methods is very, very much the same as the methods of Woodward. And you see here, it's exactly the same game. You just take a vector bundle and associate to them certain characteristic classes. And they say that, okay, the image is described by this equation and is injective if H4 has no element of order 2. And then more or less you describe uniquely your vector bundles over your manifold, which is not spin. But as I said, this doesn't hold for S5 because the second Stiefel-Whitney class lies in H2 with coefficients in Z2, right? And this is 0 for S5. So this is what I wanted to consider now. I want to consider a manifold, 5-dimensional manifold, which is spin, namely where which has a spin structure. This means the tangent bundle of M has exactly this property here, which I told you here. And I just write for short that the second Stiefel-Whitney class vanishes because I already assumed that the first vanishes because it's an oriented manifold. And now I will not consider all vector bundles here. So in my work, I considered all vector bundles, but I will consider this sub case of vector bundles, the subspace or a subset of vector bundles, which are of the following form. Well, you take a vector bundle over your manifold with spin structure, and then you take only those which have also a spin structure, or which are spinnable, which admit a spin structure, and also where the fourth Stiefel-Whitney class is 0. As, I will tell you later why this is important, but if we restrict to this class here, we have a very nice description of W. That's the point. That's why I'm restricting to these cases. But the other cases can be handled too. Okay, and then this is the Theorem of Proof. It was published in this year, but I mean, I did it 2 years before. You know how long it takes until things are getting published. And the claim is the following: that this set here actually it has a group structure. It's very interesting. It's not that obvious to see the group structure, and it is a group. And as a group, it's isomorphic to 2 times the fourth cohomology group of M with coefficients in Z plus a Z2 factor. And how this correspondence is made, I have to explain you in the next slides. Right. So we take only here elements of the fourth cohomology group, which can be divided by 2. And we see here in the example of S5, of course, as I showed you above, this is just from if we come from another way, from the viewpoint of homotopy theory, we know that there are two vector bundles over S5s, the trivial one and the tangent bundle, and this coincides, of course, with this here, this isomorphism here, because H4 is, of course, 0 for S5. Right? We have only this two factor, and I won't explain you how you can distinguish these two. So actually, this invariant here will just do exactly that. What fails in this case, it will decide which bundle do you have of these two, right? This was the main question here, right? The characteristics classes cannot do it, so we need another invariant to distinguish the tangent bundle of S5 from the trivial bundle. Okay.
Sorry, can I ask a question?
Yeah, sure.
So here you say it has a group structure, and before, because you identify, like as a result of Woodward, like he also identifies these vector bundles in terms of the cohomology group, so you can also see their group structure.
Yes, exactly. Yeah.
Exactly. And are they in any way compatible? Like, I don't know, I take my manifold and then cross it with S1 and stuff like that? Or
I didn't think about it, but yeah, it's a good point again. Didn't think about it, but it would be worth just to think about. Yeah, yeah, it's a good point. Okay, so how do I want to approach this problem to enumerate these things? Well, we have to go again use our homotopy theory here, and what I'm saying is that W is roughly the same as the homotopy class from M to BSU2. And what is BSU2? I tell you first what BSU2 is, what it classifies, and then how this correspondence is made. So what is BSU2? You can think of BSU2 as the complex rank 2 vector bundles over M, such that either the determinant bundle is trivial. Equivalent to that is that there exists a complex volume form on your complex vector bundle, or equivalent to that is that C1 is 0. Right? C1 of your complex vector bundle here is the same as C1 of the determinant bundle, and this is trivial, thus this has to be trivial, and this is all equivalent. So this is a subclass of complex vector bundles of rank 2. So this is what it classifies here. Again, with the same methods I told you before. And how is this correspondence done? Well, you can show there are some things to work on it. So if you have a rank 5 vector bundle oriented over your 5 manifold with this condition, then you can show that V is isomorphic to this complex vector bundle plus a trivial vector in a unique way. So there exists exactly one isomorphism class of complex vector bundle rank 2 with this condition here, plus a trivial vector which gives the isomorphism here. So of course you have here a complex vector bundle, and this is a real vector bundle, but you just take the realification of this complex vector bundle, and then you get a real isomorphism here. All right. So to understand this one here, I have first to understand this one here. Right. What possible candidates do I have for this decomposition here? And now here's come where the nice part kicks in on homotopy theory. Well, if you do a little bit of this magic up there with the Grassmannians and the classifying spaces, you will see that BSU2 is the same actually. SU2 is Lie theoretic the same as SP1, and so the classifying space in this case can be determined. So it can be shown that this is just HP infinity, right? And this is again the same, right? You take this is the quaternionic projective space. You have again here a chain of inclusions of quaternionic spaces, and then you take a topological limit, and then you get a topology on here, and you get again the space as a classifying space. But important for that is the CW structure which it's had, and this is just, you start with the CW structure with an S4, so you have of course a 0 cell. Then you attach a 0 cell 4 cell, which then gives you a S4, and then there's For a long part, there's nothing, and then it comes just an 8 cell, right? And then a 16 cell, and so on and so forth. But because of this CW composition, we know from elementary homotopy theories that you can restrict your, if you have here your homotopy classes from here to here, it's the same by CW approximation or by cellular approximation. It's the same as to look at the maps from M to the 5 skeleton of this thing here, or the 6 skeleton, I'm not sure. I think this is 6 skeleton of this here, because this is 5-dimensional, you need here the 6 skeleton. And the 6 skeleton of BSU2 is the 6 skeleton of HP infinity, which is of course S4, right? And then we end up with classifying, so determining the maps, the homotopy class of maps from M to S4. And this is known as the 4th cohomotopy group of M. You see, of course, if homotopy would be if we exchange the rows of M and S and the sphere, right? We get a homotopy group, and but in this order, we get a so-called homotopy group. And the homotopy groups are very much more delicate than the homotopy groups. Thomas, you want to ask something because you're unmuted?
Yeah, maybe. So this HP infinity, is the cell structure correct? Shouldn't I have a 12 cell instead of a 16 cell?
Ah, right. Oh, that's a good point. Thank you very much. Yeah. Yeah. So it's a 12 and then a 16 cell. Thank you. I have to go to layer 1. Yeah. It's always plus 4, right? Oops. All right. Yes, and cohomotopy groups or cohomotopy sets are a little bit more, I would say, nasty than homotopy groups, because first point, they not always are building a group. So they're a group. So if your dimension of your manifold is n, then pk of M is a group if k is smaller than 2n minus 1. So not only in that case it is a abelian group. In other cases it's just a set. So this is a big disadvantage in compared to homotopy groups. But on the other case, they have a very nice description in terms of so-called Bordism theory, which I want to scratch M now. Okay, so how can one compute this set of homotopy classes maps from M to S4? First of all, let me show you the whole picture. So what I'm doing here is actually true for just the nth homotopy group of a manifold of dimension n+1 when n is bigger or equal to 4. So actually I wrote 2 papers on that. So the one which just concentrated on the classification of vector bundles dimension 5, and then I just extended this type of computation here to arbitrary dimension. But I'm sticking here to the case of n equals to 4 because I just introduced this problem with classifications. Yeah. Okay, so we have an obvious map from pi4, so for the 4th homotopy group to the 4th cohomology group. And how is it? So this F is just a map from M to S4, and what you can do is you can just pull back a generator of S4 to H4, right, of your manifold. This is what you get here. So for the experts, it's just this map is just induced by the map from S4 into KZ4, right? This is just the map induced by this one here. Okay, or dually, you can see it dually, which is also very nice in my opinion. What you can do is the following: you just take a map here from M to S4 and just pick a regular value, right? A regular value is a point in S4 such that the pre-image consists of points such that the differential in this point has full rank. And if this is the case, the inverse image of this point is always a submanifold, in this case of dimension 1. And by a lemma of Sard, this regular values always exists, right? So the set of regular values is so we call a point in S4 a regular value if the inverse image is if the image consists of points with full rank, and we call it the critical if it's not a regular value. And by lemma of Sard, we know that the set of critical values is a null set in S4. So there are a lot of regular values. And if you just pick one, you just take the submanifold of it. Maybe I should put here some brackets. So you have a one-dimensional submanifold here, and then you take just the corresponding. You have a oriented. You have an oriented one-dimensional submanifold in M, and you just can take a corresponding homology class. And this is independent of the choice of x0. Right? If you choose another one, another regular value different from x0, then you end up with a homotopic map to F. And this is not that difficult to picture. Maybe I show you this in a, because the idea is not that hard to understand why this point doesn't matter. So we have here, let's take, like we have here our manifold. This is M, right? And we have here S4, and we have here a map, which is F, and we have here the pre-image, and we have here x0, and here, let's say this is the pre-image, right? This is F minus 1 of x0. And I show you a special case. Of course, the general case is much harder, but the special case is if you take another point here, let's say y0, and you know you can connect it, let's say with a geodesic here, when you connect it to this 2 point by a geodesic, such that no point here is a critical point. So every point here on this geodesic is a regular value, right? Then you can do the following to get a homotopic map here, which has the pre-image. So this, of course, if you take F minus, if you take this one here, it has a different pre-image, but this corresponds to an image, a pre-image of a homotopic map. You just rotate this sphere from here to here. By this rotation, you get a different map here, but this is homotopic, right? And in each point, what you do here, you rotate this, take a rotation from here to here, and at each point, you have a regular value, and this defines a so-called bordism between them. And if there are bordant, I tell you in a minute why this is bordant, but if you have a bordism between these two one-manifolds, they define the same homology class. But this is what you get, how you get the homotopic map. It's just the rotation from here to here, more or less. Okay, and we can show that this map here is surjective. So you can deduce this also from this one here, but there's also a geometric interpretation of the fact that this map is surjective. And why? So first of all, it is a homomorph. I didn't tell you what the group structure is. Maybe I come to later to this point, but trust me, there's a group structure on it, and with this group structure, this is a homomorphism. And this homomorphism is surjective in the following sense. What you can do, just take any homology class in M, and you know this homology class by some general theorems, you know this homology class can be represented by an embedded one-dimensional compact manifold. And if you put a little bit more work into it, you can also assume that this one-dimensional compact manifold is connected. Okay? Can always assume that this is represented by a connected one-dimensional submanifold of M. And then since M is oriented and the circle is always also oriented, right? The embedded manifold is also oriented. We know that the normal bundle must be also oriented. So what we have again here, we have a normal bundle. We have a bundle over our S1 manifold over a circle, and this has to be trivial, right? So the normal bundle of C in M has to be trivial, and so we can choose any framing on it. Right? We choose any framing, and I claim now, if we take the submanifold and a framing of its normal bundle, then we can produce such an F, which gives us exactly this homology class back. And this is the so-called Pontryagin-Thom construction. So how does this work? So what is the situation, right? So we have this normal bundle. This is an abstract normal bundle, but if we choose a framing, we have a concrete isomorphism between this normal bundle with C times R4, right? And there's also in differential topology this theorem about the tubular neighborhood, which means that, so let's pretend this is our circle here, and we know that there is a neighborhood out of it. There's a neighborhood of this circle here, such that this neighborhood is diffeomorphic to a neighborhood of the zero section in the normal bundle, right? So this red thing here is diffeomorphic to a neighborhood of the zero section in this normal bundle here. This is called usually the tubular neighborhood theorem. Okay, so what you can, then you can just assume the thing, because everything is compact, you can just say, okay, I take just the corresponding disk bundle, I replace R4 with a disk, and this is now, this represents a neighborhood of my circle here, right? So now I want to produce a map from this manifold to S4. And now I tell you first how I map the points in the red, and then I tell you how I map the points in the green. So what I do with points in the red region, so I assume I have a point in the red region here, which is not on the boundary here, just take a point in the interior. Then I map it through my identification of my neighborhood into my normal bundle, right? Then it lies somewhere here, right? Some of the disks here along C. Then I just take a projection, then I have some point here, right? So if I start with a point here, I have it here, and then I end up here. And then what I do, I just have here D4, I forgot to write it here. So this is just D4, right? And then I can go by collapsing map to S4. I'm just collapsing if I collapse the boundary of this D4, I just go to S4, right? This is the usual collapsing map to produce from a disk a sphere. Yes, and then I end with this point somewhere, let's say here, right? And under this identification, the circle will map into the center of D4 and will correspond to this blue point here, right? Okay, so I handled all the points in the interior of this red region. And what do I do with the other points here? I just map it. I might just map them here to the green point, which is the collapse of this boundary, right? The boundary of this one here is mapped to this point here, and this gives you a continuous map, because if you're here, right? If you have a point here, it maps here, and if you go to the boundary, you still stay here. But if you go from the boundary into the interior of this, you just get a continuous map from here to this point here, right? So this produces, so I put only a submanifold, the circle in here, with a trivialization of your normal bundle, and then I produce a map from M to S4. And this is called the Pontryagin-Thom construction. And I'm a big fan of this construction, because it's a very beautiful thing to produce a map from one space into another, and then to translate problems from here to there. Okay, and as you see this map, so of course now I just told you how to produce a continuous map, but for example, if you look in the book of Milner, the topology from a differential viewpoint, he constructs this map also in a differentiable way. So you construct it in that way with cutting functions, bump functions. He produces a smooth map from here to here. And you see the pre-image of this blue dot here is just the circle, right? So I produced a map from M to S4 with pre-image, and I have a regular value, and this pre-image is just exactly the homology class I started with. Okay, so in that way, this map is surjective, right? for every homology class, I found an F. And this Pontryagin-Thom construction is very interesting because it established a one-to-one correspondence between the cohomotopy group here and the normally framed Bordisms of one-dimensional submanifolds of M. And what is this? So this is not an easy maybe concept for if you see it for the first time to understand, but you can use to it, and it's very visually. You can explain it very visually. So what is this thing here? So these are just pairs of one-dimensional submanifolds with a framing of their normal bundle. Right? I have one-dimensional submanifolds everywhere, and they have normal trivial bundles. So everything is oriented here, and you just take a framing, and you mod out a certain equivalence relation out of it, and you say two of this normally framed one-dimensional submanifolds are the same if there exists a two-dimensional submanifold of M cross 0, 1, such that this has a boundary, and the one boundary is just exactly C0, and the other boundary is C1. This is the picture up here. So this is M. M is just one of the sides here, and this is M cross I, right? So, and this is W, right? So the one boundary is C1, the other boundary is C0, and the other boundary is C1. So this is one part of the definition when they are equivalent, and the other part is that this thing here, the normal bundle of this W in M cross 0, 1 should be trivial, and it should have a framing such that the framing of this normal bundle, if you restrict it to this C0 here, you get the framing you started here with, and if you restrict it here, you get the framing here, right? So this is the equivalence relation. So you have to prove, of course, this is equivalence relation, but yeah, this is indeed one. And if you only look, so if you just say that, if you just forget about the framing of the normal bundle, if you say that this W2 is an oriented manifold such that it induces the right orientation on C0 and C1, then we say that C1 and C0 are oriented bordant. And this is exactly what H1 is. You can look at H1 as the Bordism classes of one-dimensional submanifolds which are oriented bordant, right? So two one-dimensional submanifolds are representing the same one-dimensional homology class if there is an oriented Bordism between them two. Okay? And they represent the same normally framed class if there is a normally framed Bordism between them. And the whole constructions I showed you here, right? What we did here, we took an element here, right? We took just a submanifold here, C, with a framing on a normal bundle, and we produced a map out of it. And this map, which goes from here to here, which is the Pontryagin-Thom construction, this is just a bijection. You can prove that this is a bijection. Okay. Okay, let me summarize what we have so far. So we have we know this map here. This is surjective, right? This extends also to 0 here. Thus we get a short exact sequence here, of course, if we put here the kernel of this map. And this kernel of this map can only be 0 or the trivial group or Z2, of course. So why? Because if you have an element which lies in the kernel of this is just a one-dimensional submanifold which has a homology class 0. This means that it bounds a two-dimensional submanifold in M cross 0, 1, where this two-dimensional submanifold doesn't hit the end of this manifold here. So it would look like this one, right? The only boundary is just C0. This means that this homotopy, means that this is homologically trivial. But in any case, you can only put two framings on them. At most two framings. This is what I told you before the break, right? Over S1, the normal bundle can have at most 2 framings, right? And because of this correspondence here, we know that this is in 1-to-1 correspondence with this here. We know that this homologically trivial 1 manifold can have only 2 framings. Thus, this can only be 0 or Z2. It can happen, of course, in this manifold that there are 2 framings over the circle are normally framed border, right? This is what we have to prove that it doesn't occur. Right? And how do we do this? We do this in the following way. We show that the kernel is Z2, and we show it that way that we construct an homomorphism kappa from pi4m to Z2, such that if I restrict this to the kernel of this one here, this is an isomorphism. Right? It's just you can prove this. So you just take the element here, C with a framing which is not the trivial one, right? And then you just prove that it's an isomorphism. And if you have this, you have automatically a splitting map for the short exact sequence here. So this map goes from here to here, and it's an homomorphism. So it splits this short exact sequence, and you immediately get that pi4 of m is the kernel plus h1 of m, because this kappa is a splitting map for the short exact sequence. And don't get me wrong, I don't name this kappa after myself, like after Konstantis. I just named it because of the Calvert invariant. So I will not talk this about today, but if you look in my paper, you see this invariant has a strong connection to the so-called Calvert invariant. This is a certain Bordism invariant, which is also very interesting. Okay. Yes, let me serve you a side dish, just to stay in the picture of food when we're talking about in the break. So what does it have? So how do I see the bundles in this picture, right? So of course I just made this connection here, and then somehow the bundles disappeared more or less, but they didn't disappear. So let me show you how they don't disappear. In the following way. So we know that S4 is nothing else as HP1. This is just the quaternionic projective space in dimension of dimension 4, but it's just HP1. And as a projective space, it has a tautological bundle, right? What is the fiber over a point here? So a point here is a line in the quaternions, and over this line, the fiber over this line consists of just the point of this line itself, right? This is the tautological bundle. So this is and this serves as a universal bundle for this vector bundles here, meaning that every vector bundle with structure group SU2, let's say, right? Every complex vector bundle where C1, for example, or the determinant bundle is 0, you can get it by pulling back this tautological bundle to M by a map from M to S4. And then if you have this one here, if you have this interpretation of your bundle, so every bundle here is a pullback of the tautological bundle, then this correspondence here is just nothing else than I just assign to this pullback bundle its Euler class. This is just a small computation you have to do, right? So this correspondence is just take this complex rank 2 vector bundle and assign its Euler class. And this here is the tool picture. It's just taking the Poincare duo of the Euler class, right? So this is just taking the bundle, the pullback bundle over it, taking a section which is transversal to the 0 section, take a 0 locus, and its 0 locus is exactly the preimage of a regular value. Okay, so this is the connection to the explanation of the Euler class I told you before. Right, so this is so this is how you reconstruct the bundles over it. Although we are now in the complete homotopic theoretical setting. Right? So this is so again, this is just the Euler class, and this is just the 0 locus of a transversal section. Okay, and what does kappa do? This is a little bit tricky, and I cannot explain in every detail, but I hope to get the idea right. So what will this do? So I identify pi4 of M by means of the Pontryagin Thom construction with this normally framed submanifold. So I just, instead of looking at functions or maps from M to S4, I'm just looking at one-dimensional submanifolds with the framing in the normal bundle. And where am I? Here. And I will assign to every such normally framed submanifold a so-called stable framing. And what is the stable framing? The stable framing is produced like the following. So just start here in the blue. What we have the tangent bundle of M. If we restrict it to our one-dimensional submanifold, we know it's trivial. And we know a little bit more out of it. We assume that M is a spin manifold. It has a spin structure. And because it has a spin structure, it comes with a certain trivialization over your circle, right? Because there's a spin structure. This is how I define spin structures. So this is a canonical way to identify this trivial bundle with R5. So this is the left one. So I have an isomorphism with I5. If I go to the right side, I know the tangent bundle of M over C splits into the tangent bundle of C plus its normal bundle. And I have a framing coming with my F. And this framing gives me an identification with this normal bundle with R4, with a trivial bundle, with a four-dimensional trivial bundle. And what I have now is I have an isomorphism of the trivial bundle of dimension 5 with this bundle here, this isomorphism. And this isomorphism is usually called a so-called stable framing. And when you do a little bit of this yoga of stable framing and stuff, and if you do this, you end up with the following. If you have this situation here, if you have a one-dimensional submanifold with such an isomorphism, right? This gives you a stable framing, and this can be identified with a normally framed with a Bordism group of normally framed one-dimensional submanifold of S5. Okay, this is just again a black box. You have to believe me, but this is just how you get a so-called stable framing, and what you can do with a stable framing. So it's an element here, and this one here gives us with the Pontryagin construction. This is just the fourth homotopy group of S5, but since I have here only spheres, it's the same as just the fifth homotopy group of S4, and this is known to be Z2. So we are here in the so-called stable range of homotopy groups, and this is just Z2, right? So in this way, this is the proposition here. In this way, I took an element here and I produced an element in a Z2 group, right? And the sense that I took this normally framed submanifold and assigned a so-called stable framing. So that roughly you can think of the stable framing that it is a framing where you forget the ambient manifold, right? You somehow forget the ambient manifold and just look what the framing is doing, right? This is a stable framing. And this has just the property that it is a homomorphism. So by the way, how can you the group structure here is very easy to picture. And this, of course, transfers to here. So this is the one way to see that this is a group. And there's another way, more an homotopic theoretical way. I won't tell you only this way here, the group structure on this space here. Well, what is the addition of in here? It's just if you have two normally framed submanifolds of dimension 1, you just take the union. If you take the union, you can, if they intersect, you can homotope them, so you make them disjoint. This is also this is nothing else that putting them transversal to each other, because transversal means also they cannot be, if they don't intersect, they're transversal. So you can deform them a little bit, so they're disjoint, and then you just take the union of these both with the union of their framing, and then you get addition on this thing here. You can show that this is a group structure. So in that sense, this thing is here as group structure, right? This is then now the homomorphism is here more clear, because if I picture this as the normally as a Bordism group, right? I just take the union of two normally framed submanifolds, and then there's still here the union of two normally framed submanifolds under this identification. Okay, and then I can show that this. So I can show that kappa takes different values on the two elements of the kernel, right? And this means that this is an isomorphism. And thus we have that this short Isaac-Seaton splits, right, into pi4 of m into h1 and this Bordism group here. And the identification, yeah.
Is the subscript correct there?
Say it again.
Sorry, the subscript.
Right. Oh yeah, because I'm thinking at the moment a lot of the generation of this case where I have always the two here. That's why I wrote two, but that's true. It's just one. And now I can also explain how this isomorphism works. It's just either you write here H1 or homology H1 or cohomology H4. Well, what you do is just take here a map, take the pre-image of a regular value, then you get a homology class, and then take also the stable framing of the corresponding normally framed submanifold, and then you get this isomorphism. Okay, so far we understood this set here, right? This is the set of complex rank 2 vector bundles over M with determinant bundle trivial. And then we have, if we go back to this problem here, if we want to define this here, we see that, so you can compute that this condition here we have with the fourth Seyfert-Whitney class vanishing implies that the Euler class, so this one here, the dual of this one in H4, the Euler class mod 2 has to be 0. Right? So the relevant complex vector bundles for me for this classifications are only those who have 0 Euler class if I considered it mod 2. If I reduce the coefficients to Z2. And these are precisely the classes which are divisible by 2. This is what I'm writing here. So actually this is not exactly precise. So this is just the pre-image of the kernel of the coefficient homomorphism from Z to Z2. This is what I mean here, but it's roughly this one here, right? And this is just the classification of these vector bundles. And if you drop this condition here, you see that so if you drop this condition here of W4, you see that this vector bundle, I didn't write this down, but it's in my article, you can see that these vector bundles are uniquely determined by their Euler class, right? So this is the other part which I didn't write down. But if you drop this condition here, then it's just determined by characteristic class again.
I'm a little bit confused about the degree. This is the Euler class, not of the bundle that is set out, but the complex part of it or something like this.
Exactly, yeah. So this is again, this is why I wrote here E. So this is just V. I said that to every V, I have a unique E plus trivial. And this is the Euler class of this trivial one. Okay, so you see here, there's a property of this invariant which has nothing to do with characteristic classes. It's just an invariant of this vector bundles, which was needed to decide, well, in the case of vector bundles over S5, which is trivial and which is not trivial. And let me explain you a further property of this invariant, which is here. This is the last thing I'll tell you for today, so I'm a little bit short, but I hope that's okay. And what is the property of this? So this is also a very geometric property. I told you that if you have a vector bundle of rank n+1 over a manifold of dimension n+1, then you know that this vector bundle has a section if and only if the Euler class is 0 of this bundle. So if we reduce here the rank of the vector bundle with respect to the dimension, so we go one further, the Euler class does not tell you always if this is 0, doesn't mean that there is always a non-vanishing section. In topology, we say there's another obstruction. So there needs another invariant which tells you if this is 0, then it has a no vanishing section, and this is exactly this kappa. So so you can define this invariant for such kind of vector bundles. We did it for n equals to 4. We did it, right? We did it here above. When n equals to 4, we did it. But it gets also more. It is more general, right? And this kappa tells you if the Euler class is vanishing and this kappa invariant is vanishing, then you have a nowhere vanishing of this rank n vector bundle of n+1. So this is more or less a little bit a geometric meaning of this invariant. All right, and that's all what I want to tell you. Thank you very much for your attention.
Thanks a lot. It was a very delicious talk. Are there any questions at this point? Maybe I should actually stop the recording.